Let's jump right into this explainer. Today, we're looking at exactly how the physical geometry of a railway line completely dictates the safety and control of massive transit systems. We're going down to the rails themselves to uncover the fascinating physics that actually makes safe travel possible.
Here's our roadmap for this session. We'll start with the permanent way interface, then tackle gravity and gradients, move on to curvature and cant, and finally wrap up with moving tracks, specifically switches and crossings. Let's get to it.
All right, Section 1, the permanent way interface, more than just metal.
We need to start by busting a really common misconception about the rails themselves. It's easy to look at them as just static pieces of metal resting passively in the dirt. But the physical track, what engineers call the permanent way, is actually a highly dynamic environment. It actively interacts with the train. Every single second of a journey, the track geometry is either fighting or assisting train movement. What this means for us is that all our complex signaling and control systems have to be perfectly, mathematically adapted to this geometry just to ensure trains stay safely apart.
Moving on to Section 2, gravity, gradients, and braking, the vertical challenge.
Let's look at our first major obstacle and see exactly how the system handles the vertical challenge of gravity. Picture trying to stop a massive 700-ton freight train. Well, gravity dictates that downhill slopes or falling gradients absolutely require increased signal spacing. Why? Simply because that train needs a much longer braking distance to safely come to a halt. On the flip side, uphill or rising gradients let you use shorter signal spacing because gravity is actively helping to slow the train down. But engineers have to be incredibly careful here. They have to actively avoid placing signals partway up a steep rise. If a heavy train is forced to stop mid-climb, the time it takes to accelerate again is massive, not to mention the severe risk of wheel slip if the weather turns bad.
And this really highlights the extreme precision required. When dealing with track-based train detection systems, engineers have to calculate clearance points with incredible accuracy. Take a look at junctions. The placement of insulated rail joints or axle counters actually has to account for the physical overhang of the train. That's the distance between the wheels and the absolute end of the vehicle. If a train is braking on a gradient, the signaling system absolutely must know if that overhang is going to foul an adjacent line before the train fully stops. We're literally talking about a game of millimeters and rock-solid safety margins.
Now here's a super clever engineering trick you probably haven't noticed on your morning commute. In modern metro systems, stations are frequently deliberately built at the top of a rising gradient. They're intentionally using gravity to help slow the train down as it rolls into the station. It's a brilliant structural manipulation because it massively reduces the mechanical braking effort required, which in turn reduces the sheer amount of heat generated by those brakes in an enclosed underground tunnel. So instead of fighting it, they're making the geometry work for the system.
Okay, Section 3, navigating curvature and cant, the lateral challenge.
Having conquered the hills, we now turn our attention to the lateral challenge of navigating corners. Track curves create huge obstacles for what we call signal sighting, which is just the driver's ability to clearly see the signal from a safe distance. This gets exceptionally tricky in urban or underground environments, where tunnel walls just completely block the view. But it's not just about signals. Curvature severely impacts the safety of track workers, too. It makes placing line-side telephones highly dangerous, simply because staff trying to access them can't see fast-approaching trains coming around the bend.
So the crucial concept to grasp here is cant. Cant is basically the slope of the track across the rails, essentially banking the outer rail higher than the inner rail. They can elevate this outer rail up to 150 millimeters to let trains maintain higher speeds through corners. But as you can guess, this physical manipulation has a massive ripple effect. It dictates the maximum permissible speed on the line, it completely alters where signals can be safely spaced and sighted, and it even creates major headaches for routing trackside cables. Literally every adjustment to the track geometry ripples through the entire control system.
Finally, Section 4, moving tracks, switches, crossings. Let's look at the immense mechanical challenge of physically changing a train's path while it's moving. A simple set of points, or switch, relies on 4 rails in total. You've got the 2 outer rails, the stock rails, which are completely locked and fixed in place. Then you have the 2 inner rails, the switch rails, which are the ones that actually move side to side. For a train to safely pass, one switch rail has to perfectly touch the stock rail, while the other leaves a precise gap for the train's wheel flanges to glide through. As you can imagine, it takes tremendous force to reliably divert the massive weight of a train like that. To pull this off safely, modern automated point machines follow a really strict, non-negotiable 4-step sequence. First, unlock the points. Second, drive them to the new position. Third, Lock them securely in place so no amount of vibration shakes them loose. And fourth, detect their precise position. The control system, known as the interlocking, has to mathematically and electrically prove that all 4 of these steps are 100% complete before it will authorize any train movement over those tracks. No exceptions. Whether we're talking about a simple crossover between 2 parallel lines or a highly complex switch diamond for high-speed junctions, the interlocking system takes absolutely 0 chances. It relies on these highly precise individual detector rods attached to the point blades. These rods continuously feed the exact position of the blades back to the system. So if those blades are slightly out of position, or if they're blocked by even a few millimeters of loose ballast or debris, the rods prevent the electrical contacts from operating, and the signaling system instantly halts any approaching trains.
Which brings us to a frankly surprising safety feature of track geometry. Sometimes the absolute safest action a control system can take is intentional derailment. Yeah, you heard that right. Take a look at these catch and trap points. Catch points, like the spring or wide gauge variations, are actually designed to deliberately derail loose runaway wagons running against the normal direction of traffic. Trap points do the exact same thing for trains trying to leave a siding without permission. The system intentionally forces them off the track and into the ballast before they can reach the main line and potentially cause a catastrophic collision with a high-speed passenger train. So, to wrap up this explainer, I want to leave you with a thought for your next commute. Next time you travel, look down at the rails outside your window and ask yourself, is the physical track assisting your journey today with perfectly banked curves and gravity-assisted gradients? Or is the signaling system working overtime in the background just to safely fight the limitations of the geometry? It is a fascinating, constant battle of physics happening right beneath you.